Okay, so hi, my name's Robert Beverly. I work for MCI WorldCom on the VBNS, and I'm here to just talk about really quickly some work we're doing in the multicast space. So some history on the VBNS, really just a quick slide. We're an NSF-sponsored network, this National Science Foundation, and part of that charter was to do end-to-end performance tests and to verify the performance of the network. So as a extension of that idea, we developed an analogous test for multicast. The end-to-end unicast tests that we've done traditionally have used cron jobs to run things like mping and Trino, TTCP, and other tools like this to verify the performance. It's a lot more difficult in a multicast network when you have some number of senders and, of course, multiple receivers. So developed a protocol to actually control a number of end hosts to synthesize traffic and receive traffic. So some details on the VBNS multicast network. And in each of our POPs, we have about 13 POPs. We have a Sun Ultra 2 with an OC12 NIC, and this connects with a direct PVC/30 to a local Juniper M40. The M40s have POS, and now they're all OC48 links across the country, and ATM backup links. The POS links are always preferred, and this is a PIM sparse mode domain. So the protocol was designed to allow maximum flexibility. So there's essentially a daemon that runs on each of these Sun hosts and listens for control instructions, whether to receive packets, send packets, or so on. So there's a health check message. There's a message that says, okay, send some number of packets of some size on some particular group at some particular rate. And then you would, in conjunction with that, have to tell all of the receivers to expect to receive some number of packets on some group. So the way the test would work is that a coordinator, a central coordinating host, would go ahead and check the health of all of the daemons on the boxes, and then it would select one sender and 10 receivers across the country. The coordinator would then send control instructions to the receivers, telling them to go ahead and expect to receive these packets on some group. The receivers will then open the socket, and the IGMP membership will be sent. The coordinator then will send the transmit control instruction to a single host, who will then begin transmitting. The receivers during this time collect loss information and misordering information. So each packet actually has a sequence number in it, and it can detect which packets were lost. So the receiver will wait for the last expected packet, or will time out waiting on the last expected packet, one way or the other. And the coordinator waits for acknowledgments from all of the receivers, and then it gathers the loss information and generates some nice graphs and HTML on our web page, and then select a different transmitter and repeat. And this is done every night on the VBNS. So some more details on the test. The addresses that are used for the multicast are selected from this RFC GLOP space. It's all administratively scoped, and a lot of people ask why you're doing this with ATM. So almost all of our customers currently come in via ATM. This is mainly for historic reasons. We already had these Sun performance hosts deployed in all of the POPs with good connectivity, OC12 connectivity, and it's easy to control the traffic rate. So this is just some nice animation with everything I just said. So there's the instructions to tell the receivers to expect some number of packets, an instruction to tell the sender to send, and then the sender will start sending, and just really quickly, the way it works is that it will encapsulate this in an RP register message and unicast this to the rendezvous point of this sparse mode domain. He'll build S-G state to the source to pull the traffic, and then it will flow down the shared tree, which will initiate the SPT switchover, and a real SPT, shortest path tree, will be built. And then when all the receivers finish, they will send the information back to the coordinating host. So the nightly results are available on this URL. So both absolute time relative loss, and you can see the nature of the loss, whether it's bursty or continuous, etc. And then finally, we also have the passive OC XMONs, which are optically split our backbone trunks, and all of the data is verified with the OC XMONs. So here's a tabular report from a few days ago, and this is what gives a summary of all the performance. So the loss numbers are very small. This was run at, as you can see up in the corner, at 10 megabits, about 50,000 packets in fairly large packets, and there's really negligible loss. We also just recently are able to SNMP poll our routers for the multicast state and packet counters and things like this. We weren't able to do this. They finally got the SNMP code in to do that. So you can actually see the shape of the tree by doing some recursive SNMP polling. This is just a Perl script that does this. And you can see the amount of time that state's been installed and some packet counts. And it should follow that the sites that are farther down the tree obviously should have more loss than the ones closer to the source. So here's some examples of the graphs that are generated. So you can see in the upper picture there's some bursty loss, whereas in the lower hand picture there is really only 2 periodic losses there. And I can't entirely explain this, but these are the type of characteristics we see on our network. Still negligible loss for all intents and purposes. So for us, these have a lot of practical applications running every night. There's an email that's sent out. So we can detect performance problems in the network. We can determine the multicast performance, and we can also detect multicast routing anomalies and other weird things. We actually had a tunnel pick disappear out of one of our production routers during a maintenance window and detected it this way. And then, of course, so some causes of the loss are the initiation time it takes to install state, obviously in the multicast network, a congested path, routing instabilities. So some practical problems we had just for a NANOG audience, things that might get you. There's currently no way to get the IGP routes, the OSPF routes is our IGP, into the Juniper multicast rib. So we were forced to do some route map type activities to get these routes into BGP, because this was breaking the RPF check. IGMP membership reports, there was an issue where that actually has to be an optioned IP packet. And we on the VBNS have the luxury of running multicast natively on our backbone. So the same routers that attach customers are also running multicast codes. We don't have an overlay network, and this has bitten us in a number of cases where the routing daemon on the Juniper will crash because of a multicast related issue and bring down the box. So the extension of this is we've now done this at fairly high data rates, from 1 sender to 10 receivers, sent 1,000,000 4K byte packets at just under 400 megabits per second. And this was really just a proof of concept. I think if multicast is going to have any practical application in, say, the arena of video delivery and things like this, they need to be able to have very high performance. So this particular router we're using performs very well, namely in part to the shared memory architecture and not having to do the packet replication. And right now the speed is only limited by the performance of the Sun hosts, and those are only really packet per second limited. So if we had faster hosts, we could do even better. Wanted to mention some other things that can do very similar things. The Netcom systems came out recently with something called Smart Multicast IP. which does very similar things, probably everything that I've just talked about. There's the Multicast beacon, which is a useful debugging tool, and also MRM, which is the Multicast reachability monitor. Some URLs for those, and some references for some IETF type benchmarking documents for IP multicast. And we're going to try to do some higher rate testing, perhaps with the Netcom systems boxes with GIGI interfaces. The nice thing about the SUNs is, as I said, they're all deployed. They're fairly high data rate. It'd be nicer to get above 400 megabits, but this may be difficult. Going to try to do some group capacity testing, seeing the number of groups and latency involved in various things like this for the state. And some of this terminology comes directly from the IETF RFCs, the mixed class throughput, so on and so forth. And that's all I had for you. Sure.
It's question time, so think of your question. You showed a page that showed the test results of SNMP polling, and you said you could see the shape of the tree.
Well,
what did that mean?
So yeah. If I can get back to that. Okay. So the shape of the tree is essentially the root. The root node here, it recurses. It's a Perl script that recurses up, so it knows every end host, and it says, okay, so who is your upstream neighbor? And then it will go ahead and poll, SNMP poll its upstream neighbor, and so on and so forth. So you can see the root, and then below that is the next person in the tree and the next person in the tree. This script really should be written to, do something graphical or something much nicer than this. This is just a rough cut. And obviously could be presented in a much nicer fashion. So.